Hi, this video is about proving limits from the definition of a limit. We have a question here. Using the definition of the limit at infinity, prove that the limit as x approaches infinity of 6x plus 1 over 2x minus 1 equals 3. Well, what is the definition of the limit at infinity? We have that right here. We say that the limit as x approaches infinity of some function f of x equals a number L if for every epsilon greater than 0 there is some number m such that for any x bigger than m, then the distance between its function value and this number L is less than epsilon. And graphically we have this situation. We have a function f and we have its limit L, and we can see that the curve does approach that limit as x goes to infinity. Now this inequality, on the left hand side, this expression, the distance between the function value and the number L, that is the distance between this line L and the blue curve. And epsilon, where is that on our graph? Well, I've chosen a couple of sample values here, epsilon 1, epsilon 2, and epsilon 1 is the distance between the line L and the dashed line L plus epsilon 1, and it's also the same distance between the line L and the dashed line L minus epsilon 1. So this inequality is the same as saying that the distance between the line L and the blue curve is less than the distance from the line L to the dashed line, and also the distance to the lower dashed line. And that means that the blue curve is between the two dashed lines. Now the idea is that for any particular epsilon that we've chosen, that we find some number m so that for all x values bigger than m, we get that condition holding. So say if we've chosen epsilon 1, then I've chosen m1 that works, because from this point onwards the blue curve is always between the two dashed lines. And if instead we'd chosen epsilon 2, then I've chosen a value of m2 that works, because from this point onwards the curve, the blue curve, always stays between the two dotted lines. And if we can do that for any epsilon that we choose, no matter how small it gets, if we can always find some m value on the x-axis where the blue curve will from then on always stay between the two epsilon lines, then that proves our limit. Okay, so let's have a look at our particular problem now. So we'll let f of x equals our function, which is 6x plus 1 over 2x minus 1, and also L equals our limit, which is 3. We'll start by fixing some arbitrary value for epsilon, which is greater than 0, and we'll begin by looking at this distance from the function value to the limit L. F of x minus L equals, in our case, 6x plus 1 over 2x minus 1 minus 3. Okay, we'll take a common denominator of 2x minus 1, and we get 6x plus 1 minus 3 times 2x minus 1 all over 2x minus 1. Now we'll simplify the numerator. we have 6x minus 6x and 1 plus 3, which gives us 4, over 2x minus 1. Now, because we're interested in x values that approach infinity, we're allowed to set any minimum value for x that we like. So I'll suppose that x is greater than 1. Now, I've chosen the number 1 for a particular reason, and I'll talk about that in a little while. But to start with, if we have this condition of x greater than 1, then we can say that 2x minus 1 is always a positive number. And that means that this fraction is positive, and then we can remove the absolute value signs. So let's do that. We'll say then fx minus L, absolute value, is equal to just 4 over 2x minus 1. Now I'd like to simplify this a little further, so I'll say that that number is less than 4 over x, and that is since if x is greater than 1, which I've just supposed, then our denominator 2x minus 1, and I can rewrite that as x plus x minus 1 is greater than x, because x minus 1 is a positive number. So we have that this denominator is bigger than that denominator, so the fraction is less than that fraction. Now next we can say that this value 4 over x is less than epsilon if and only if 4 over epsilon is less than x. And we can see that if we multiply both sides of this inequality by epsilon and then divide both sides by x, then we get back to this inequality here. So now we have what we're looking for. We've got a lower bound of x such that this condition holds, that this distance between the function value and the limit is less than epsilon. We can bring m into the answer now and say that we choose m equal to, well, we'd like to set m equal to 4 over epsilon, but we have to remember that we've specified that all our x values must be greater than 1. So we can't allow m to be less than 1. So one way around that little problem is to say m equals the maximum of 1 and our value 4 over epsilon. Then if x is greater than m, then, well, firstly we know that x is greater than 1, and that means that all our logic is valid, and also x is greater than 4 over epsilon, which means that epsilon is greater than 4 over x, which is greater than this distance. So we can say that that distance is less than epsilon. And this is what we're trying to show. So this proves the limit. I'll just make a few comments now about the simplification that we've done here, because it can be a tricky little part of problems like these. Firstly, about this choice of a lower bound, I've chosen 1 here, and that's for a couple of reasons. One was to allow us to remove the absolute value signs here, and secondly to let us apply this logic to make this simplification step. And in other problems, depending on what function you're working with, you can choose any particular value for a lower bound that will make your life easy in doing these steps. But actually, for this particular problem, this simplification here, it's not really necessary. You could also do it this way, which is to say that 4 over 2x minus 1 is less than epsilon if and only if 4 over epsilon is less than 2x minus 1, which is true if and only if. We'll add 1 to both sides here and then divide both sides by 2, and we get a half plus 2 over epsilon is less than x. So that gives us a lower bound for x, and we choose m equal to max of 1 and our new value, which is a half plus 2 over epsilon, and then we complete the answer as we did before. And this method here is just as good as the method we used up here, but this type of simplification, it becomes more necessary when you have more complicated functions, say with high degree polynomials or trig functions, for example. One other thing I'll mention is suppose if instead of 4 over 2x minus 1 we had 4 over 2x plus 1, then with the plus there our simplification becomes a lot simpler. We can say that that's less than 4 over 2x because we've reduced the denominator, which increases the fraction. So then we can go on to say, well, that's equal to 2 over x, which is less than epsilon, if and only if 2 over epsilon is less than x. So we have a lower bound for x there, and then we complete the answer as we've done before. Okay, well that's all I'll say about this problem. If you have any questions or comments, please leave a comment below, and thanks for watching.